One of the perks of being in a special topics course is that if you request a topic that is within the instructor's area of expertise, then there's a chance that he or she will talk about it in class if you want to know more about it. So for example, last semester during the measure theory seminar, there was a guest speaker that was talking about his research, and his research involved BMO functions, which, if you're not familiar, BMO stands for bounded mean oscillation. I think it's a topic that is discussed more in probability theory textbooks because I haven't really come across the term too many times while reading my books. For example, this one, functional analysis book by Stein and Shikarchi, I got this from the library and I really wanted to read it, but I was unable to find enough time to really get into it. I think I only really read the first chapter. And in the first chapter, he talks about BMO functions, although it's just a surface level discussion. I believe BMO is also kind of talked a lot about with respect to martingales and Brownian motion. I'm not entirely sure. But when I took probability theory, I don't remember BMO ever really coming up. Or maybe it did, the instructor just didn't call it that. So I got interested in BMO, and I asked the instructor if we could talk about it next semester, which is this semester, and he agreed to, although he didn't cover it until like last week. So we're just now getting into BMO. I still don't understand a lot about it. I mean, I can understand the definition and everything, but actually working with it is another thing. So he gave one homework problem that was related to BMO on Thursday of this week. No, it was Tuesday, sorry. He gave it to us on Tuesday. And I have been playing with it on and off since he gave it to us because I still need to do at least 2 homework problems in the class. And unfortunately, only the problems that are left are pretty difficult. Or at least they're difficult for me. And I think I need to go to him for some help because ChatGPT couldn't answer anything I was asking it. Stack Exchange is weird for me right now. I don't know why I can't post questions. But I did give it an honest attempt, and I thought, well, may as well turn to YouTube, see if someone can say anything that can be helpful. But all I'm going to do in this video is discuss what I've tried and where I'm, what issues are arising. How come this thing isn't being solved? So let's talk about the problem itself. So this is the problem. We have a function f from real numbers to real numbers that's a locally integrable. We can assume that there exists a universal constant alpha positive such that for any finite interval, so I did not write finite interval, but it is a finite interval, nothing up to infinity or negative infinity, such that there exists a measurable subset E with the following 2 properties. The measurable subset E is bounded below in measure by alpha times the measure of I, and f minus fi is bounded above by 1 in absolute value on the set E. So I should have written here what fi stands for, but it's the average value of f over the interval I. So written mathematically, this is what fi is here. And I also defined this number ci to be the same, except I'm putting absolute value around f, in case I needed the notation. So the claim is that f is a BMO function. So I've said BMO like 13 times now. What does BMO stand for? BMO means that if I take the supremum of this expression, so we have 1 over measure of I times the integral over I of f minus fi dm, where m is the Lebesgue measure. If I take the supremum over all possible intervals I, if this is uniformly bounded, meaning if this is uniformly bounded, so that if I take the supremum, it's still finite, then we say that f is a BMO function. So this is what I want to show. And my approach was to just look at the expression without supremum. So I've written that here. And I want to find a bound for it that is independent of I, so that if I take the supremum of both sides, then I'll have the supremum as bounded, and I can claim that f is BMO. So how am I going to do that? Well, the first thing I did was I took the expression and I split it up into two pieces. So the first piece is over e, and the second piece is over I get rid of e. So I call this expression a and this expression b, just to make notation easier. And a is pretty easy to get a handle over, because when we're in a, f is being evaluated over the set e, which means that this expression in absolute value is bounded above by 1. That was because of the assumption that we have here. So I can replace this with 1, and then I'll have integral over e dm divided by measure of I, which means that the left-hand side is bounded above by measure of e over measure of I. So that's what I have written up here. And since e is a subset of I, we know that this ratio is bounded above by 1, and 1 is independent of the interval I. So it's not too hard to get a nice bound for a. The issue comes from trying to get a handle over b, because how do you get a handle over I get rid of e? Well, when I'm stuck on a homework problem like this is kind of what I try. So I just write down all the things that I know, and I try and use little hints that the instructor kind of gives us in the class. So I know that the measure of I get rid of e is bounded above by 1 minus alpha times the measure of I, which follows from 1, the first assumption that we have. And he also made mention that it might be helpful to look at the proof of the John-Nirenberg theorem. So what is John-Nirenberg? I don't really want to get into the statement of John-Nirenberg, but it uses this trick of splitting I into dyadic intervals. So this is me trying to recreate that argument, but I'm running into a snag. So just as a reminder, if you're not familiar with dyadic intervals, we take this interval, we split it up into two smaller intervals that are of half the size of the original, and then you just kind of keep going for each subinterval that you create. So for the first interval, I'm going to call it I0. In the second when we refine, we call them I sub 1. So 1 just tells us, so this index that appears here is the stage of refinement that we find ourselves on. And then the index that appears in the superscript represents the index of the subinterval. It tells us which subinterval we're talking about. And we're going to read from left to right. So this is the first one, this is the second one. And then if you refine again, we'll call this one the first, the second, the third, the fourth. And if we refine again, then we have 1 through 8. So that's how I label the intervals. And what I'm going to do is look at sets and stopping sets and not stopping sets. And I'll define what those are in a second. So the first thing we do to make life a little bit easier is I'm going to create some more notation for I get rid of e. I'm going to call it f, just so that I don't have to write 3 symbols every time. I'm just going to write f. And then I write fnk to be the part of f that's in ink, because I don't really know where the set f is. F could be just this horrible monster that's just all over the place. So these dyadic intervals kind of give me a little bit of control as to what part of f that I'm talking about, which is denoted fnk. So if I union all the fnk's together, I will get f. So what do I want to do? I want to stop refining the intervals when the average value of f minus fi over the set fnk is bounded below by some constant number that I can pick. And I put 2 to the n here just because I was trying something. I don't think this 2 to the n thing is really the way to go after looking back over this. So really, I've lost my pen, so I'm not going to erase it. But I don't think this 2 to the n business is really the strategy. But I can put a number here, right? So let's say I put like 1 here or something. Then we know that outside of the stopping intervals, or really just the stopping sets, we know that the value of f minus fi in absolute value has to be bounded above by that same constant that appears here, because this, remember, is the average value of f minus fi over the stopping sets. So outside the stopping sets, it has to be bounded bounded above by that stopping number. So if you union all the not stopping sets together, so remember, I'm taking f and I'm splitting it into the stopping sets and the not stopping sets. So if I union all the not stopping sets together and then evaluate this integral 1 over measure I, then this guy can be replaced with whatever constant that appeared here. Pull that out and add up how many times it occurs, because I need to know how many times fnk occurs for not stopping sets. That can be pulled out here, and then the measure of this union is going to be bounded above by 1 minus alpha measure I because of this guy that shows up here, which means that this expression can be can be bounded above by 1 minus alpha measure I all over measure I, which came from over here, plus whatever this constant is that I add up so many different times. And so the measures of I will cancel. This number that appears here is some constant depending upon, if I chose 2 to the n, for example, it's some constant depending upon n. And if I can show that I'm not adding up too many of these 2 to the n's, meaning like infinitely many, then this bound is independent of I, and for the not stopping sets, I should be okay. But there's my first issue, is I don't really know how many of these fnks, these not stopping fnks are, at least at the time being. If I just replace this with some number like 1, for example, then how many 1s am I going to be adding up here? I have to make sure that I'm not adding up infinitely many 1s. So there's my first issue. I don't really know how to choose this constant that shows up here very well, because I really want to get rid of anything dependent upon I over here so that I can get a bound for this expression over the not stopping sets. And then comes the issue of how to get a bound for this expression over the stopping sets. Because, well, I tried to repeat an argument that showed up in John Nierenberg, but it just wasn't happening. I don't think the argument really works that shows up there. But the idea is this. I know this much at least. I know that f minus fi is locally integrable, because I know f is locally integrable. So if I subtract fi, whatever this average value is, it should still be locally integrable. And what I can do is try and make this union of stopping sets have arbitrarily small measure. So my strategy is not so much controlling what f minus fi looks like, but controlling the set of integration. Because if I can make the set of integration arbitrarily small, I should be able to make this integral small. So it harkens back to uniform integrability, I think, or at least that's what I want to try and do. But I've been stuck on this since yesterday and the day before, which is when I really started to work on that. I'm sure this problem is easy for someone watching this video, but it's not easy for me, and I need to read more about it. I mean, I went to the internet just to try and see, if I could find anything that could help me point me in the right direction, but my issue lies with trying to figure out how to make sure that the not stopping sets aren't too numerable. At least I think off the top of my head that's what I want to do, and how to make the measure of the union of these sets arbitrarily small. So I'm not seeing it right now of what to do. It is also possible that this strategy that I'm applying here is not the way at all that you want to go. But this is kind of what I think the instructor was alluding to a little bit. So I'm trying to think creatively about it, but I'm not really seeing what to do immediately. I'm sure once I see the answer, it'll be like, oh, how come I didn't think of that? But I'm really just trying to use all the tools that I developed while I was preparing for my qualifying exam. Like, maybe I can get a bound on F minus Fi. If not, can I get a bound on the set of integration? Can I split up the set of integration into nice pieces that I have more control over? Can I multiply by 1 in a creative way, or add or subtract 0 in a creative way? I don't know. I hope the problem isn't too easy, because otherwise this video will be embarrassing, but I think he sounded like this problem wasn't the easiest to do, although I could be not understanding him correctly. But anyway, that's what I thought. I thought about making a video about BMO. It sounded pretty interesting, at least at the time, and he gave us this homework problem. So hopefully I'll be able to get this completed by Thursday and present it to the class then. Anyway, thank you for watching.